First, let me thank the organizers. Excuse me for a slightly long title. This is the work done with Priyanka Bhoyer, who works in a local college. When I was in Nagpur. So Kuramato model is kind of Bohr model of nonlinear dynamics, you can say. It works very well as it is for Josephson junctions, for metronomes, for electrochemical oscillators. If you add inertia, it works very well for power grids. If you add phase differences, it works very well for optics. It is rare to find a model, a simple model, which works very well for many experimental situations. So it has become very popular. And this is, I have never worked before, but I worked in Kuramato for the first time. So this is submitted work, not yet published. And most of the works are with positive couplings. Although experimentally you also see negative couplings in some particular cases. This is not much experimentally motivated, but I go for a negative coupling and one-dimensional chain of Kuramato oscillators. This is what I am studying. Now, what is the nature of coarsening and defect dynamics for antiferromagnetically coupled Kuramato oscillators? That is the point. So the equation goes like something like this. Basic equation is phi dot is equal to omega. I have taken identical omega. Usual Kuramato oscillators have disorder in omega plus k times right hand side plus left hand side and sin phi I plus 1 minus phi I, sin phi I minus 1 minus phi I. This is the equation and k is less than 0. I understand that the oscillators are periodic boundary conditions and they are identical oscillators. I start with random initial conditions. Now if I start with this in random initial conditions, I will just show you what happens essentially after a very long time for any k less than 0. For any k less than 0. This is not for some critical k value or something like this. That basically you see zigzag patterns and then there is some discontinuity at 0. This zigzag pattern breaks down at phi equal to 0. Then again you have zigzag kind of patterns. Then again a discontinuity at phi equal to 0. And suppose I make a kind of order parameter. Order parameter is the following. That if site 27 is bigger than site 26, it is a plus spin. Site 28 is less than site 27, then it is minus spin. Now if for the zigzag pattern, the sum of consecutive spins should be 0. Otherwise it will be minus 2 or minus 1. So modulus of sum of consecutive spins is order parameter, and this particular order parameter shows number of defects in this particular zigzag order. So I point to this, and then how do these effects evolve in time? If you look at these effects evolving in time, usually the defects show in for Ising or such kind of models, they show kind of random walk, and then they coalesce, they random walk and then they coalesce, and it is not like this. These are almost kind of circular smooth kind of patterns, and then these trajectories intersect, and then finally some particular type of defects emerge. So if you look at this, how these defects reduce in time as a function of time, it goes like 1 over t raised to 0.25. Okay, 1 by 4 is the exponent, and then they saturate. Finally, there is a saturation. There are certain asymptotic set of defects as we see, and then they are roughly equidistant, and then you can say that this is something like topological. I mean, this phi equal to 0 does not distinguish, and they stay there forever. But this particular size at which the saturation occurs does not go like n raised to 4, although the decay is t raised to 1 by 4, it goes like n square. Okay. So the defect density goes like t raised to minus 1 by 4, and finite size saturation is like n square. So z is equal to 2, delta is equal to 1 by 4, not 1 by 2. That is the thing. So there is annihilation via this slow kind of, whether it should be glassy or not so glassy is a different matter, but this is the different thing. Now we also looked at persistence. Persistence, we looked at slope persistence, that if site 7 was bigger than site 6, so it has plus spin. So how long it stayed plus spin before becoming minus even once. So number of sites which did not make a mistake until time t, I mean they did not deviate from the right path even a single time. All those, this is of course a monotonically decreasing function. This is known as persistence, and this persistence does not, I should not say exponent, persistence goes like a stretched exponential. It goes like exponential minus c t raised to 1 by 4. So it goes like a stretched exponential, and this particular exponent, I mean exponent inside the stretched exponential, this is 1 by 4. You can have some kind of argument for this. So for field as well as slope, so the field stays beyond, above the average or below the average, you can find the same exponent and you switch into 1 by 4. You can do finite size scaling, as this is known to the community, that if something goes down like saturates like n square, you divide by n square to the defects and you go take the 1 by 4 proper, then there is a collapse is obtained. Now from the equation, sin theta I minus theta I minus 1 and sin theta theta I plus 1 minus theta I and theta I minus 1 minus theta I, you can expand sin theta. If you expand sin theta, then you will get plus minus theta x, because right hand side and left hand side will constant. So all things will cancel and you will have a kind of continuum theory which says that delta t by delta phi is something k times del x square plus del x raised to 4. Now if you can do answers, e raised to ikx plus omega t, and you will get omega of k is modulus k times kappa k square minus modulus k upon 12 times k raised to 4, because modulus k is positive, k is negative. Now this is just like the first talk, you remember, omega was the k square minus k raised to 4 plus something, it was there. So there is a value at which d omega by dk is 0. This is the fastest growing mode, which turns out to be something like root 6. So 2 pi upon k star is like 2 point something. So you get stability at around 2. Okay, so you can say that this particular continuum theory explains this particular thing. Now this k raised to 4 explains 1 upon t by 4. T raised to 1 by 4, and k square explains the power 2. Okay, so you can take this these things, and so this leads to t raised to minus 1 by 4. So quartic operator controls early time, and k square tells you why this is this thing. Now if you do it in 2 dimension, the 2 dimension antiferromagnetic coupling, the whole thing shows t raised to 1 by 4 decay, but this decay saturates at some particular finite time, and that particular time is not n square or something, it is not independent of n, it is some value which is determined by system, and it saturates forever. So there is a finite time saturation and global order fails. So what happens is that there are defects in this direction, there are defects in this direction, they somehow lock in, and once they lock in they don't move, and so at some particular finite time there is a the things are saturated. So these are the results. So in 1D dt goes as t raised to minus 1 by 4, z equal to 2, stretched exponential persistence. In 2 dimension there is no long range order, and these are the conclusions.
Thank you. Let's thank the speaker. Questions?
This is a generic question. Like in the slide before this, you had this 1 by 4 exponent for dt.
Yeah.
And for this persistence also you had 1 by 4 exponent.
Yeah.
Are these two exponents connected?
These two exponents are somewhat related. For persistence, you can do some kind of hand waving, this thing. This survival thing is very well known in survival statistics, is very well known in statistics community. It is exponential of some kind of hazard rate, that you have not encountered the hazard till particular time. Now this hazard rate can be done like this, that you have this size of order t raised to half, then the decay is like t raised to minus 1 by 4, so hazard is, so the number density of active occurs is 1 by 4, then per unit time is minus 3 by 4, you integrate, you get 1 by 4. There is a small calculation, I will show you.
Thank you.